Hi, my name is Lizader and I'm developing a brand new Sony PlayStation 1 game, which looks like this. PlayStation 1 is a very limited platform, but despite its limitations, it's indeed capable of producing mind-boggling effects. There's a lot of charm and character in the graphics it produces. Dithering, wobbling polygons and textures, limited color palettes. It all makes PS1 games look unique. Learning how PS1 works and developing games for it is a very fascinating process. I plan to make in-depth videos explaining how I develop my game in the future, how I program it, the bugs I struggle with, all the custom tools I make, how I make my models and levels, how I make the graphics look as good as possible, and so on. But today we'll take a look at how Silent Hill and other games simulate fog. You'll learn a lot about PS1 graphics and its GPU. I implemented Silent Hill's fog in my game and it made it look a lot better. I used an emulator called PCA6 Redux to study how Silent Hill and other games work. It has a very useful feature called GPU locking, which allows you to see which commands the GPU did to draw the last frame. This was all I needed to reverse engineer Silent Hill's fog. No decompilation was necessary. All the PlayStation 1 game footage in this video was recorded from the PS1 itself. I also went an extra mile and made all the slides you're about to see run on PS1 as well. After all, the best way to show how things work on the platform is by showing it on the original hardware. The ISO for the slides is available for download on my itch.io page, so you can check it out on your own PS1. Fog is an important aspect of making a game look good. It makes games more atmospheric, makes the levels seem bigger, and sometimes it can make a game pretty creepy. It can also be used to hide poor view distance and model popping. Fog also makes the games look more three-dimensional. It simulates what's called aerial, or atmospheric perspective. The further away the object is from the camera, the more it fades into the background, and the less saturated it becomes. This makes it easier to judge the distance between your character and other objects in the scene. PS1 games use various approaches to fog simulation. To me, Silent Hill's fog is the prettiest out of all of them, but it's also the most complicated and resource intensive. But first, let's take a look at how a simple fog can be implemented on modern GPUs. And by modern, I mean GPUs from the last 25 years or so. In the modern graphics pipeline, you usually have a texture called the depth buffer. This texture contains the information about the distance from the camera to the closest object for each pixel of your screen. For example, the objects close to the camera have their depth value close to 0, and faraway objects have their depth values closer to 1. Given the current camera transform, we can calculate the distance from the camera to the closest object. In this example, the cat is roughly 5 meters away from the camera, and the background is 16 meters away. First, we compute the fog factor using the following formula. Here, fog density is a parameter which takes values from 0 to 1. The closer to 1 it is, the denser the fog becomes. If the object is close to the camera, the computed fog factor value will be close to 1. If it's further away, it will be closer to 0. And finally, to compute our final color with the fog edit, we interpolate from the fog color to the original color of the image without the fog. If the object is close to the camera, we'll have a fog factor value close to 1, and the final color won't be affected by the fog much. The further away the object is, the closer its final color will get to the fog color. However, you can't use this approach to implement fog on PS1. First of all, it doesn't have a depth buffer. But even worse, the PS1 GPU doesn't support shaders. Its functionality is fixed and you can't efficiently perform per pixel calculations. Despite all this, PS1 games still manage to achieve convincing fog effects. Let's see how they do it. Let's start with the simplest approach to fog on the PS1. It's called CLUT, or Color Lookup Table Fog. It's used in many PS1 games, such as Ace Combat 3, Mega Man Legends 2, and LSD Dream Emulator. The basic mechanism of this approach is simple. All we have to do is change the textures palette for each polygon we draw. The further away the polygon is from the camera, the more faded the colors get, and the closer they become to the fog color. PS1 has 1 MB of video memory. It's basically a 1024 by 512 pixel texture, each pixel containing 16-bit color. VRAM is divided into 32 texture pages, also called T-pages. Each T-page is 64 by 256 pixels. The frame buffers, which are used to draw and display the game on the screen, are stored in the VRAM too. PS1 supports multiple render resolutions. A lot of games use 320 by 240 pixel frame buffers, which already take almost a third of your VRAM. As you can see, VRAM space is very limited. One way to make the most out of available memory is to use indexed images. When we draw a primitive, we can tell the PS1 GPU to interpret a texture page as an indexed image. The GPU will use some part of VRAM as a palette and interpret another part of VRAM as indices into this color lookup table. In 8-bit indexed color mode, one indexed pixel takes up 8 bits of VRAM. In this mode, your palette can be 256 colors at most. You can fit a 128 by 256 pixels texture into a T-page. There's also 4-bit indexed color mode, which limits your palette to just 16 colors, but it allows you to store textures up to 256 by 256 pixels, 4 times more than if 16-bit color was used. Mega Man Legends 2 mostly uses 4-bit textures for its characters and environments, which makes it possible to fit a lot of the textures into VRAM. When you draw a primitive, you can use any color lookup table uploaded to VRAM, not just the original palette that the texture was uploaded along with. We can use this to simulate fog. First, we need to prepare additional palettes for each texture in the scene. We take the original textures palette and then make multiple palettes by interpolating the original texture colors to the fog color with different interpolation factors. The closer to 1 the interpolation factor is, the more faded and closer to the fog color the palette becomes. 8 or 16 CLUTs are usually enough. Each polygon we draw will use a different palette, depending on how close it is to the camera. If it's very close, we use the original palette. If it's further away, we use another palette with more faded colors, and so on. This effect is very efficient on PS1. However, it's not perfect. First of all the color lookup tables can take up a lot of VRAM space, since you need to store multiple CLUTs for each palette of all the textures that your game uses. Secondly, it's not very smooth. It's easy to see the points at which different CLUTs are used, and it makes the ground and walls look very polygonal and grid-like. Compared to the Silent Hills fog, where the shading is smooth and fog gradations are not as visible. Another approach to fog on PS1 is fading faraway polygons to black. It's used in games such as Kingsfield 2 and Hell Knight. As you can see, this approach produces a fairly smooth fog, especially compared to the CLUT fog. PS1 can draw flat shaded polygons and Meguro shaded polygons. With Meguro shading, you can set the color of each vertex of your polygon to a distinctive color, and then PS1 will interpolate the color of each rasterized pixel between them. Textured polygons can also be Meguro shaded. When PS1 draws a pixel of textured Meguro shaded primitive, it first samples the original texture color and then just multiplies it by the interpolated color from the polygon's vertex colors. The color 128, 128, 128, which I'll call neutral color, doesn't change the texture's colors at all. If you set the color to a bigger or brighter value, such as pure white, the texture gets overexposed, which can be useful for making highlights and specular effects. When you set vertex colors to black, the texture disappears completely and you get a black polygon. If you set some of the vertices to black and some to neutral color, you get a nice fade out effect, which looks especially good on black background. Let's see how we can make this work with multiple polygons. One interesting aspect of the PS1 GPU is that it only works with 2D primitives. You need to manually compute the screen coordinates of each 3D vertex on the CPU before sending the primitive to the GPU. PS1 has a special coprocessor called GTE, or Geometry Transformation Engine, which helps you do this efficiently. To transform the vertex from 3D space to screen space, we use a GTE command called RTPS, or Rotate Transform Perspective Single. When we use this command, we not only get X and Y coordinates of the vertex in screen space, but also horizontal distance from the camera to the vertex, called screen Z. Another useful thing we get from RTPS is the depth skew. Here's how it works. The depth skew is 0 for vertices whose screen Z is smaller than the camera's near clipping distance. If the screen Z of the vertex is larger than the far clipping distance, its depth skew will be equal to 1. For vertices in between the clipping planes, the depth skew is a normalized screen Z value, which goes from 0 to 1. To achieve fade to black fog, we want the vertex color to be close to a neutral color when the vertex is close to the camera, and get progressively closer to black color the further away it is. GTE has a command called DPCS, or Depth Skewing Single. This function performs a linear interpolation from input color to another color, usually called far color on PS1. All we have to do is interpolate from neutral color to black using the depth skew which RTPS command gives us. Do this for every vertex in the scene, and that's pretty much it. This fog looks pretty good and smooth, and works especially great for dark and creepy scenes. However, it has one major limitation. You can only fade to black with this approach. Let's see what happens if you set the far color to a lighter color, which Silent Hill uses. As you can see, it doesn't look that great. Here's why. With vertex colors, we can only modulate the texture. We can make it darker or brighter, but we can't make the texture colors fade to some fog color. To do that, we need to do something a bit more complicated. Let's finally see how Silent Hill's fog works. By the way, Legacy of Kain Soul River uses the same approach as well. Here's what we want to achieve. If the polygon is close to the camera, we want its texture to be unaffected by the fog completely. If the polygon is further away from the camera, we want the texture to fade out a bit and become closer to the fog color. Finally, when the polygon is very far away, we want the texture to disappear completely and the polygon's color to be equal to our fog color. In other words, for vertices close to the camera, we want the vertex color of our textured grow primitive to be neutral and for the fog component to be black. For the vertices with depth skew of, let's say, 0.5, we want the texture to fade away, which can be achieved by setting the vertex colors to a darker color, but we also want to add a bit of the fog color on top. And finally, for vertices far away from the camera, we want the texture to disappear completely. This can be achieved by setting vertex colors to black. The fog component, on the other hand, should become equal to fog color. The vertex color of a textured primitive is interpolated from neutral color to black using the vertex's depth skew, and the fog component is interpolated from black to fog color using the same depth skew value. To combine the texture and fog components, we'll use additive blending. Normally, when you draw a primitive on top of another, the foreground primitive pixels completely replace the background ones. When you draw a semi-transparent primitive with additive blending, the background color and the foreground color get combined. This is exactly what we need for our fog to work. First, we draw an opaque untextured polygon. Then, we just draw a semi-transparent textured polygon on top. We then repeat the process for each polygon in the scene, using the formulas below. This approach works beautifully. The fog is smooth and doesn't have those discrete steps that CLUT fog had. With this approach, we can set the fog color to whatever color we want, and make the fog more dense or sparse by changing our near and far clipping distances. This approach fails when you try to use it with a texture with transparent pixels. We draw a non-textured polygon before drawing the textured one, so it doesn't take a texture's transparency into account, which is not what we want in this case. Let's see how we can fix this. On modern platforms, the colors are usually stored as a 24-bit value, 8 bits per color component. On PS1, we usually store color as a 16-bit value, 5 bits per color component. The remaining most significant bit is called semi-transparency bit. It performs multiple functions. Let's say you draw some primitive on the screen, and then draw a semi-transparent sprite on top. If the all semi-transparency bits of the frog texture are set to 0, the blending won't be applied to the sprite at all. If they are all set to 1, the whole sprite will become semi-transparent. We can make only some parts of the sprite semi-transparent. We can set the semi-transparency bit for only some of the texture's pixels. Normally, when we draw a primitive, the texture semi-transparency bits will be used to replace the semi-transparency bits of the frame buffer. Drawing a textured polygon with textured semi-transparency bits equal to 1 will set the corresponding frame buffer's pixels to 1. If you draw a sprite with a texture which has semi-transparency bits unset, the corresponding semi-transparency bits in the frame buffer will get replaced with zeros. Note that the pixels corresponding to the transparent pixels in the texture will not affect our frame buffer at all. If you want the PS1 GPU to set semi-transparency to 1 for each drawn pixel, no matter which STP the texture has, you can use a special primitive called mask control with force set bit equal to 1. Let's say we draw a texture which sets some of the frame buffer's semi-transparency bits to 0. Normally, when you draw a texture on top, it will draw the whole primitive, no matter which semi-transparency bits the frame buffer has. If you add a mask control primitive with check bit set, it will only draw new primitives on the pixels of the frame buffer which don't have semi-transparency bit set. You can think of the pixels with the semi-transparency bit set as write protected. Here's how we should draw polygons with transparency in their texture. At the frame start, we draw the background with fog color with force set mode enabled. This will set all the frame buffer's semi-transparency bits to 1. Then we draw our tree polygon. It's important for the textured pixels to have the semi-transparency bit be equal to 0. After we draw a polygon with the tree texture, the corresponding frame buffer's pixels will get their semi-transparency bits set to 0. Now, all we have to do is set the mask controls check bit and draw a semi-transparent and textured polygon on top. The fog will only affect frame buffer pixels corresponding to the tree's pixels, which is exactly what we want. The last piece of the puzzle is how to efficiently draw characters. Drawing the geometry twice is very expensive, and usually characters have a lot of polygons in them. So, Silent Hill does the following. First, it draws the character without the fog component applied. All the character's textures should have the semi-transparency bit unset, just like when we draw the tree. Once we have drawn the character completely, the corresponding semi-transparency bits of the frame buffer will be set to 0. So, we can set a check bit of mask control primitive and draw a semi-transparent and textured quad on top, which will make the character appear to be faded in the fog. And this is how Silent Hill fog works. It's very resource intensive compared to the previous approaches. You need to draw double the polygons for all the static geometry. Secondly, you need to use semi-transparent polygons and additive blending, which adds additional overhead. Still, this is my favorite approach to fog on PS1. It just looks great. And that's it. Hopefully this video was informative and useful for understanding how some parts of the PS1 GPU work. If you enjoyed the video, you can also follow me on Twitter, where I regularly post my PS1 game development and random PS1 related stuff. And if you really enjoyed it, consider buying me a coffee on Ko-fi. There are many other mind-boggling effects that I'd like to explore in the future. For example, how Bass Rice achieves its incredible water effects. Or how Metal Gear Solid simulates motion blur in its cutscenes. Or how dynamic lighting is implemented in Silent Hill. There's a lot of fascinating stuff left to explore about the PS1 and its games. So, stay tuned. See ya!